So in this video, I will show you how to generate an SVE, and here you see an example of an SVE. And the model in MATLAB uses this software for visualizing the SVEs. So I will go through about this software a little bit more in detail later on, but this is basically what the model looks like, an SVE. So it's a cube of any size really that you choose, and the blue surfaces here, or the blue volume, is cement, and the red part here is aggregates. So we can filter out the cement. Yes. Okay, so now the cement has been filtered out, and unfortunately, this software ParaView only renders half of the model unless I move it around like this. But you see here the aggregates and the way they are resolved in terms of voxels, these very, very tiny cubes. And the model then uses, well, the computational model uses this geometrical model to do various computations. So for instance, to compute effective diffusivities and also to do transient analysis. So to generate such a model, you go into MATLAB. So you have the class file here. And when you download it from GitHub, you also get this stationary example M file, which sits, let's see here. It sits right there. And then the class file is SVE, SVE class.m is located in this folder. So this file is this file here, and this is the file that you will use to run the model from. So you will never be inside this model file unless you want to do some implementation or changing the model itself. But if you're only going to use it and run it, you will do that from this file or any file that calls this file, that calls the SVE class file. So if we start from the beginning, it adds a few paths here. So it adds these two subfolders. So these two lines adds these two folders. And then when you create an object, which this model is treated as, you do it by this command. So SVE is equal to SVE class, and this is the same name as the name of the class file. So now there's an object that is, we call it SVE in this case. It could be anything here, but this is an object based on this class here. And what then you need to do is to set a few properties that this object will have. So these objects here, these properties are the same ones that are defined here. Okay, so any property which is you define or invoke that by dot and then the name of the property. So you have an nx and then realization number, lbox, agfrac, etc. And you all find them here. And then you set values to them here. And nx has to do with meshing that I will get back to. Realization number is if you want to generate many SVEs of the same type for statistical purposes. So if you say you want to generate many SVEs of the same size and of the same aggregate fraction, but with different distributions of gravel because of them being randomly distributed. So you can have several realization numbers. So you can set this to any number. Lbox is the size of the SVE. So this is the length of this cube in centimeters. Max time is something that has to do with the packing algorithm that I will get back to. And here is input for generating an SVE. So what these lines do is that it reads a sieve curve from this text file, sieve input.txt, and you'll find this file. Sorry, I have it opened here. So this is just a text file that needs to be located in the same folder as this file, the stationary example.m file. So this is the content of this text file, and this defines the sieve curve. So on the left column here, you have the diameters of your aggregates in millimeters, sorry. So this is diameter in millimeter, and then each fraction's relative percentage. So how much of each of these fractions you should have uh, in relative measures. Okay, so this reads the input, and then you extract the ballast radii and the gravel sieve from the two columns. And here we have to specify the number of gravels that you want. So how this method works, or this algorithm works, is that it uses the relative distribution of gravel diameter that it uses here, and then it builds a sieve curve based on the number of gravel. So this could be any number. So the higher the number, the better resolution you will have of this sieve curve. And then what it does is that uh, it within a cube, it throws in 5,000 gravels, and for each gravel, it will throw this in the cube, and then see if this piece of gravel, if it overlaps with any other previously existing pieces of gravel, and if it does, it will remove it and then try to throw it out at a different random place and see if it overlaps. And when at that point when it doesn't overlap anything, it will keep that gravel and then throw out the next one, and it will do so until it has thrown out 5,000 pieces of gravel inside this square cube. Okay, and that's basically the setup. And then there's a packing algorithm implemented. So here you set the aggregate fraction. So this is what you want to have in terms of fractions. So the aggregate fraction by volume. So in this case, I want to specify it to be 25%. So 75% in this case will be cement, and the rest will be cement. And this is something you set by yourself. And the packing algorithm starts if you define higher aggregate fractions than 45%. So this algorithm of just randomly throwing out gravels, it works up to 40-50% quite good. But if you want something like 60%, you need a packing algorithm that will pack the aggregates together. And based on this, you will have to, there's a sort of trial and error here, because you specify the size here, and you specify the aggregate fraction here, and also the number of gravel. So and if we run this now, we will see how well or how close we got to this value. Okay, and also before we run the program, we need to set the path. So this is where it will save all the outputs from the model. So now I will just put it on my desktop. You can leave this empty like this, and then it will just set the path to the path where you have this file. So all generated files will end up in this folder where this file is. But if you specify a path, you just add it like this. So now it will end up on my desktop. And then to generate the SVE, you invoke this command sve.generateSVE, and it takes these inputs. Okay, so the ballast radii and the gravel sieve and the number of gravel, these are the ones that those were extracted from this text file, and then the number of gravel is something that you define yourself. The last one is max time, and this only becomes relevant for the packing algorithm. So this is in case you want to set a specific time for it to pack the SVE, because it might take a very, very long time. So you can specify here how many hours you want the algorithm to be packing, and then if it uh, if it's still not, so when you run the packing algorithms, let's say you want to have 65%, it will try to pack this until it reaches this value. But this might take a very long time. So maybe you're satisfied with, well, you want to aim for 65, but maybe you are satisfied with 63, say. Then you estimate that this will take, let's say, 100 hours. Then you can specify 100 hours here, and then the packing algorithm will stop and save after 100 hours, even if you haven't reached 65, which was your goal. Okay, but for now, uh, we're only interested in reaching 25, and the packing algorithm only starts for aggregate fractions above 45%. So this doesn't matter what the value here is. So this is what you need to have as input for this method, generateSVE. Okay, so then we just run the program. And here now I display K here is the number of gravel that it has distributed within the model. So it will run up until 5,000. So when you run the model yourself, you will not see the output here from K. So this is just to display how many pieces of gravel we still have left. So it will run up to 5,000. And then we'll see what kind of volume fraction we got, because we specified the L box and we specified the number of gravels, and we also specified their size via this CV input text file. So the actual aggregate fraction will be whatever it will be. So this is just something that we wish for, but it's not necessarily what we will get. Okay, so I paused the videos, and now it has finished. So now we reached the 5,000 pieces of gravel, and then this is the actual volume fraction that we got. So it's only 7%. So if we want to actually have 25%, we will either have to increase the number of gravel by at least one order of magnitude, I guess, or we will have to decrease the size. So this, again, this was in centimeters. So this is something you will have to basically trial and error to tweak it, so that if you want 25%, you will either have to increase the number of gravel or decrease this one. And when you increase this, it obviously take a longer time, because then it has more pieces of gravel to distribute. Okay, but now this generateSVE function or method is complete. So now we stored all the data on the desktop. So now if we go to the desktop, we see that there is a folder here. And this, yeah, so I have something saved some before, but now what we had was, let me see if I scroll up, and then here was the folder. Okay, so we had the size of the SVE was 3, so then we have a folder called lbox3, and inside this one we have now one that refers to the aggregate fraction, so it's underscore 25 for 25%. And then we had realization number 1, so this is the one that we have. And here what's been saved now from this method is this file. So this is a binary MATLAB file that saves basically, if we go back to the model here, it saves the coordinates for each sphere in this case. So the center coordinate, the x, y, z value plus its radius. So it's just I think it's just 2 matrices, one with the coordinates and one vector with the corresponding radius. And it also stores, I think it stores some data about the SVE, the size of the SVE, for instance. So this is quite a tiny file, and this has now been generated and saved by this method. So in the next step, we will use this file to mesh the model.